Hello students, in earlier lecture we have seen how thermal sensors are designed or which are those for the measurement of temperature. We have seen the definition of temperature as well. So temperature is manifestation of thermal energy of matter, and there are various temperature sensors. We have begun with the RTD, that is resistance temperature detector. Before that we have seen that in case of solids, the atoms are not stationary, they are performing vibration about their mean position or equilibrium position. So in the case of solid as well, even if they are very strongly bounded with respect to their neighbor, still they are performing vibration, and their vibration is the function of temperature. So if temperature will increase, then vibration will increase. Similarly, in the case of when we supply energy to the solid, then the attraction or the bonding between the neighboring atom is little bit distorted. As a result of that, that bonding is loose, and therefore the atoms are performing more vibration, or the atoms will start to slide with respect to each other. As a result of that, solid is converted into liquid, and in liquid the molecules or the atoms are trying to vibrate as well as they are trying to slide within the volume or within the container. And this is valid even in the case of gases as well. So therefore, for the definition of temperature, we can say that it is the manifestation of thermal energy shown by atoms or molecule. Now over here we have begun with the RTD, that is in which we are going to employ or use how variation of resistance of metal is used for measurement of temperature. For the same we have used metals over here, and therefore we have written that is variation of metal resistance. We are making or using metal over here, so therefore variation of metal resistance with temperature. And this resistance is linearly dependent on temperature. How it is for the case of metal, that also we have discussed in earlier lecture, that if we supply energy, then the atoms will start to vibrate, and if we supply more and more energy, then atom will vibrate with more amplitude and frequency as well. So therefore the electrons will collide with respect to vibrating atom, and as a result of that they will offer a resistance. So in the case of metals, the resistance or metal resistance is the function of temperature. And therefore, for the approximation, or what is the equation which relates how variation of temperature can vary the resistance, we are having these two approximations. So the first is linear approximation, in which we have written RT is equal to R0 in bracket 1 plus alpha T minus T0. So over here you will able to notice that variation of resistance with respect to temperature is approximately linear. So therefore we call this type of equation as a linear approximation of metal resistance with temperature. On the contrary, in case of quadratic, this equation, that is RT is equal to R0 1 plus alpha T minus T0 plus alpha 2 T minus T0 square. So over here you will able to notice that the variation of resistance is with respect to square of temperature. So quadratic term of temperature is comes over here. As a result of that, we call this as a quadratic equation. Now when we shall use this linear equation or approximation, so the limitation of this linear is that if our temperature is less than 200 or for only the small span of temperature, then only we can able to use this linear approximation. Later on we will see the problem based on that. And over here this alpha is the constant, and this alpha or alpha 0 can be determined by this particular manner. And many a times this T0 is located or found out in such a way that it is located at the midpoint or at the central portion of the given temperature zone. So this was about the linear. While in the case of quadratic approximation, there is RT, that is resistance at any unknown temperature, R0, where this R0 is resistance at known temperature, and this T is the unknown temperature, T0 is known temperature, and all constants are there. So over here this alpha as well as alpha 1 in both equation is linear variation of resistance with temperature, while this alpha 2 is quadratic variation of resistance with temperature. So these are two equations that are used many a times for calculation of unknown temperature from the variation of resistance. Now let us move what are those specifications or the requirements when we use this RTD, that is resistance temperature detector. So let us begin with the what is its sensitivity. So in general, sensitivity is defined if we change our input, how our instrument is giving a response by changing its output. So therefore over here the sensitivity or figure of merit of this RTD has been defined by alpha, and alpha for most commonly used RTD, that is platinum and nickel, has been shown over here. That is for platinum it is 0.004 per degree Celsius, and similarly for nickel it is 0.005 per degree Celsius. So these values are of alpha. From this we will able to notice that in case of platinum, the resistance will change by 0.4% if the temperature is changing by 1 degree Celsius. And similar manner for nickel, its resistance will get changed by 0.5% if temperature is getting changed by 1 degree Celsius. So from this we will able to notice that which is good to use. Because for platinum, variation of resistance with temperature is less, while for nickel it is better. So from that, at least superficially you can say that nickel is better to use, because in that case variation of temperature will bring us more variation in resistance. So many a times this RTD is always defined on this data sheet of RTD. So the sensitivity is determined from the definition of alpha, where this alpha is how the variation of resistance is taking place with respect to change in temperature. So this alpha is said to be as, or it is the sensitivity of given RTD or resistance temperature detector. The next important point, that is response time. For an example, if suppose I am having a beaker and in which a water is there. If I bring my thermometer in contact with the beaker, then that beaker or temperature of water should be same as that of temperature of thermometer. So therefore some time is required for the mercury or for the thermometer in order to come to the thermal equilibrium to that of the water. So therefore some time is required to bring thermal equilibrium, and same is happening over here. The response time is important over here, and for this RTD it is 0.5 second to that of 5 second. So why is it so? Because we have written over here why slow, because it is due to thermal conductivity in bringing into the thermal equilibrium. So when we bring RTD in contact with the unknown temperature, how it's giving the response, or within how much time it giving us response, that is the response time. So for typically RTD it is 0.5 second to that of 5 second. Now over here there are two types of conditions are given. When RTD is there, that is metal is there, and therefore when this metal is come in contact with that of unknown temperature, the medium is very important. As a result of that, when this response time is taken into consideration, when there is free air, then we can say that there is poor thermal contact because air is in between the unknown temperature and RTD, while in the case of for oil bath, it is for good thermal contact. While for free air, it is having the slow because there is poor thermal contact. As a result of that, some time will be taken by RTD to bring to the thermal equilibrium to that of the unknown temperature. So therefore, for free air condition, we can say it is little bit slow. While for the case of oil bath, as oil is very good for conduction, so therefore we can say that there is good thermal contact, as well as for oil bath it is the fast response. So this time may be reduced for the case of oil bath. For the case of construction, many a times when we use this metal resistance for measurement of temperature, two important factors are there. Because when we keep this length of wire as it is, then its size will be increased. And second is it will come in the direct contact of the environment. So to avoid both these problems, what we have make over here, that is a length of wire we have not kept as it is, we have wounded on a form in such a way that it will form a coil. Why coil? Because in that case it will achieve this small size so that it will be portable. At the same time there will be good thermal conductivity, and there will be decrease in response time. If we are bringing this RTD in the contact of the unknown temperature, there should be immediately response shown by RTD. If it is taking more time, then it is of not use. So therefore, in order to reduce the response time, these 2 or 3 factors are very important. So for regarding the construction, length of wire is wounded on a form, it will form a coil, and secondly there has to be some protection, because this RTD, that is nothing but the resistance, if it is come in the direct contact, then in the case of hostile environment there will be the problem. So for the protection it need the sheet which will able to protect it from the different types of condition, that is like the humidity and so on. So therefore these were important regarding the construction. When we are using this RTD for the measurement of unknown temperature, then the regarding signal conditioning has been explained over here. We are having the bridge circuit used, or it is preferred to use for the measurement of resistance. So therefore we have shown initially that R, that is resistance, is changing approximately equal to 4% per degree Celsius. So therefore for that big variation, how we can do, that is with the help of bridge circuit. So over here we have taken one, that is resistance R1, R2, R3, and R4 is over here. So R4 is the RTD, that is resistance temperature detector. So let us write here as RTD. So these 4 resistance R1, R2, R3 and this RTD, they are forming a bridge over here. And this RTD is, we have kept in the environment in such a way that whose temperature or whose ambient temperature is getting changed. As a result of that, if environmental temperature is getting changed, then that change is sensed or measured in the form of change in resistance. If resistance will get changed, then of course this bridge will be not balanced. And therefore the output that we are taking across the point, let us say A and B, will getting changed. So over here this differential amplifier has been used for amplification of what is difference at between the potential of A and B points. So over here this RTD means resistance is get changed. That change in resistance will bring change in potential over here. That change in potential is recorded or amplified with the help of this differential amplifier. Now one thing you will able to notice over here is that every time the power supply is required over here. Without this power supply we cannot use this. So this RTD is used, and we have written that there is compensation lines. So compensation lines means extra lead wires that we have used for this measurement of unknown temperature. Why we have used those compensation lines, let us see it. For the same, if we have kept this RTD, and if there is along this RTD that we have shown over here, if there is ambient condition change, then along this RTD there will be change in resistance will be there. If that change in resistance is bringing change in our output voltage, then there will be some problem, or there will be the error will be there. In order to avoid that error, we have used this extra lead wires. We call them as collectively compensation lines, which will able to bring some changes in the arm of R3 resistance as well as in the arm of RTD, that is resistance temperature detector. As a result of that, this null condition, it will not disturb at all, and therefore this error can be minimized by using the compensation line, that is extra lead wires, in order to not changing any condition of the null, or the resistance will remains in proportion. That is regarding the signal conditioning. And for the dissipation constant, as I told you that this power supply is required. Whenever there is power supply, it means that current will be flow through the particular resistance, as well as current will flow through our RTD, that is resistance temperature detector as well. So when current is flowing, then the power will be dissipated there, and that power is given by I square multiplied by R, where I is current, R is resistance. So I square R amount of power is dissipated due to the self-heating. Now if there is self-heating, then unnecessarily temperature will be rise there, and which will bring some error, or there will be false reading will be shown by our RTD. As a result of that, this offset output will get disturbed, which we don't want. So therefore this dissipation constant also come into important, that is I square R is power dissipated due to the self-heating. So when we are making more and more accurate reading of temperature by using this RTD, we have to consider the dissipation constant, that is due to I square R, how much amount of self-heating is taking place. So self-heating means there is increase in temperature or rise in temperature due to the I square R. So we have written that is temperature rise. Why so? Because due to the self-heating. Why self-heating? Because there is power dissipated and it is given by I square R, and therefore unnecessarily due to the power dissipated there will be increase in temperature, which we don't want. It is the error. So therefore that delta T is given by P upon PD, where this PD is the constant, that is dissipation constant given or provided in the data sheet of RTD, and this P is nothing but the power. So if I, that is R, or current is more, then P will be more. If current will be less, then P will be less. So over here this dissipation constant is also one of the important factor that we have to take into consideration, and it is expressed as the watt milliwatt per second. That is, with respect to change in temperature, how much power is dissipated. That is the dissipation constant. And regarding the change or regarding the range over here, as I told you that these nickel and platinum are preferred to use because in those cases the variation of resistance with respect to temperature is more over linear, repeatable. As a result of that, we have mentioned for the case of platinum, its range is from minus of 100 degrees Celsius to that of 650 degrees Celsius, and for nickel it is minus of 180 degrees Celsius to that of 300 degrees Celsius. So for nickel as well as platinum we have mentioned over here because regarding we are using them as a RTD or for measurement of the unknown temperature over here. So this was all about the what are the characteristics or specification of resistance temperature detector, that is one of the thermal sensor. Now we are going to see how this thermal sensor can be used for measurement of temperature depending upon two problems, and in next lecture we are going to see the measurement of temperature by using the new thermal sensor, that is thermistor, in which variation of semiconductor resistance is employed for the measurement of unknown temperature. Thank you. So variation of resistance or how linear variation can be used for determination of unknown temperature. We are having a sample whose variation of metal resistance versus temperature we have taken in this table, in which the first column will represent temperature and second column will represent the resistance in ohm. So for determination of unknown temperature or for finding the equation for linear approximation, we are initially going to select the data or the temperature which is at the midpoint. For the same you will able to see that the temperature will begin from 60 and it will reach to the 90 degree, and therefore the middle, that is 75, we have selected as a T0. So T0, that is the middle or midpoint of temperature range, it is T0 we have taken. The corresponding resistance we have called it as RT0, that is resistance at T0 temperature, and this is the beginning step that we have to follow for the case of linear approximation. So once we know value of T0 and RT0, the next step will be determination of alpha, where this alpha is linear fractional change per temperature or per change in temperature. So for the same we are going to determine what is the value of alpha 0. For determination of alpha 0 we will need RT0, we will need T2 T1 and we will need R2 R1 as well. For the same, this 60 degree Fahrenheit we will take it as R1 or T1 actually, and corresponding resistance we will take it as a R1. Similarly, the maximum temperature, that is 90 degree Fahrenheit, we will select it as T2 and corresponding value of resistance will be take it as a R2, and we are going to substitute values of R2, R1, T2, T1 in order to calculate value of alpha 0. So as we know that this alpha 0 is given by 1 upon RT0, R2 minus R1 upon T2 minus T1. So we have substituted all the values over here. So alpha 0 will equal to, initially we have taken this value of R2, that is 112.2, minus of R1, that is 106.0, upon or divided by RT0, that is this 110.2, and multiply by T2 minus T1, that is T2 is 90 degree and minus T1, that is 60 degree Fahrenheit. So therefore, from that we can determine the value of alpha 0, that is 0.001875, and unit has been mentioned over here. Since temperature is given in degree Fahrenheit, so therefore this alpha 0 will have units in per degree Fahrenheit. If temperature would have given in degree Celsius, then this alpha 0 would be upon or per degree Celsius. So depending upon T, this alpha will change its unit over here. This was regarding the alpha 0. Now we know the equation for the linear approximation, and let us try to substitute all these values, that is T0, RT0 and alpha 0 for our linear approximation equation. Then we will have RT will equal to RT0 has been substituted over here, that is 110.2, and in bracket 1 plus this value has been for alpha 0. So alpha 0 is 0.001875, and in bracket there is T. So we have deliberately kept this T as unknown temperature minus of T0, where this T0, as I told you, we have selected it as a 75. So all has been given in ohm. So if we substitute any temperature between the range of 60 to 90 degree Fahrenheit, then we can determine value of its resistance, or we can determine any value of resistance in between the range of 60 to 90 degrees. So this was regarding the linear approximation. Let us try to see what happened in the case of the quadratic approximation. For the case of quadratic approximation, equation will get changed, and we are having the same data, that is column of temperature or resistance over here. So the question is that find the quadratic approximation of resistance for the data or above data, which we have seen in the earlier problem, between 60 degree Fahrenheit and 90 degree Fahrenheit. Again, the span or the range of temperature has been same, but still there is big difference. So let us see what is that difference. So here T0 is selected as central, that is 75 degree Fahrenheit. RT0 is 110.2 ohm. The initial or the first and foremost step is remains same for linear as well as approximation and quadratic as well. So T0 is known to us, RT0 is also known to us. We are having the equation about quadratic approximation, that is RT0. So over here RT0 means we are going to write equation for R at 60 degree Fahrenheit. So R at 60 degree Fahrenheit will equal to its corresponding value of resistance is 112.2, RT0, that is 110.2 over here, 1 plus alpha 1. Since now we are not having any value of alpha 1, so let us keep it as it is. So alpha 1 will be as it is, and in the parenthesis we are having 60 minus 75, because this 60 is our temperature and 75 is the midpoint temperature, and plus alpha 2, again there is 60 minus 75, but for this time we are having the square of that term over here. This was regarding R or resistance at 60 degree Fahrenheit. Again we are going to write the same equation for R at 90 degree Fahrenheit. For R at 90 degree Fahrenheit, we are written the equation as its corresponding value of resistance, that is 106.0 ohm, is equal to RT0, that is 110.2 as it is, and in bracket 1 plus alpha. Now for this time the temperature has been changed, and we have written 90 minus 75, where 75 is the midpoint over here, plus alpha 2, 90 minus 75, but for this time there is square. So two terms having the square, and there is one term which is very linearly over here. Now we are having equation number 1 and equation number 2 with us. In order to get value of alpha 1 and alpha 2, we will solve them and by adding above equation we will have the value of alpha 2. So by solving the equation we will get the value of alpha 2 as a minus of 44.36 multiplied by 10 to the power minus 6 per degree Fahrenheit square. So over here this alpha 2 is varying quadratically with respect to the temperature, and therefore we have written units of heat as degree Fahrenheit its square. So as alpha 2 once we get, then we will try to substitute that alpha 2 value in equation number 1 or equation number 2 in order to get value of alpha 1. So the alpha 1 comes out to be over here, that is 0.001875 per degree Fahrenheit. So units of alpha 1 and alpha 2 are different over here, as well as their values are also different. So let us try to substitute values of alpha 1 and alpha 2 in our quadratic equation. Then we will have RT, we are keeping capital T deliberately as it is. So therefore this RT would be 110.2, that is RT0 in bracket 1 plus this value 0.001875, we have taken it from alpha 1 in bracket T minus of 75, and minus alpha 2 value is minus of 44.36 multiplied by 10 to the power minus 6, and in bracket we are having T minus of 75 its square, and all this term has been expressed in the units of ohm. So this equation will enable to gives us unknown resistance in between the temperature range of 60 degrees Fahrenheit to that of 90 degree Fahrenheit. But for this time this equation is little bit get changed, and this equation is for quadratic approximation. So we have seen linear approximation as well as quadratic approximation. Let us try to see out of them which is good or which is better, in which the error will be minimized. For the same, we are having the same data in front of us. We will take this equation and earlier equation for linear as well, and we will try to determine what are the errors in between them. For the same, the question is in front of us. So it is, by what percentage do the predictions of linear and quadratic approximations vary from actual values? With respect to actual or real values that we have measured from practical setup, what is difference between linear and quadratic? That is the question over here. And again the temperature range is same, that is at 60 degree Fahrenheit and 90 degree Fahrenheit. So as we have seen both problems regarding linear as well as regarding the quadratic. For the same, for linear model or for linear approximation we can say we have used this equation. So therefore, since they have asked us to calculate resistance at 60 degree Fahrenheit, so therefore we have taken R at 60 degree Fahrenheit, that is resistance at that temperature. And it is given by, again the linear equation we have used, and by substituting values of alpha over here and temperature, we will get its values, and therefore we will have 107.1 ohm by using the linear model. And similarly, again at 90 degree Fahrenheit, we are having the same equation, that is R at 90 degree Fahrenheit is equal to same thing. Again by solving, we will get 113.29 ohm. Now one thing you will able to notice here is that if we actually see what is difference between this RT and that value, then you will able to notice that the error is 1.07%, which is big error over here. And similarly, for the case of 90 degree Fahrenheit, if you see the actual data or practical data with respect to this calculated data, again there is big error, that is error is 0.97 degree or 0.97% over here. So for 60 degree as well as for 90 degree, the error is 1.07 and 0.97% respectively. So it is big error. This was regarding the linear model. Let us try to see what happens whether error is increase or decrease for the case of quadratic model. Again we will try to consider the earlier equation, that is R at 60 degree Fahrenheit is equal to RT0, we have substituted over here 1 plus this value is for alpha 1, 60 minus 75, this value is for alpha 2, and in bracket 60 minus 75 its square. By solving it, we will get it is 106.0 ohm. So if we again try to compare difference between this calculated value from quadratic model and data value, you will able to notice that there is no any big difference between this value and the data value. So therefore we have written over here as error is approximately equal to, or over here it is absolutely 0%. So it means that if we try to compare linear approximation or quadratic approximation, then the quadratic approximation gives us less error or minimize error, and in the case of linear model we are getting the big error over here. So from that one can say that quadratic approximation giving us, or it provides better approximation than that of the linear one, in which error is minimized to that of the greater extent. Thank you.